Hello everyone, this is Lab 5 on stability. Let's get to it. So by the end of this lab, you should be able to figure out if your system is unstable or stable and explain why it is or isn't. So let's have this first example here. Actually, I'll start by saying the ways that you can find stability. Let's just cut to the chase. So if we have an open loop transfer function, right, this is going to like system s y of s. The poles of the system tell you if you are stable or not. So if the poles of the system determine stability, the second way is that if you have, the second way explained in his lab is if you have a state space equation like this, the equation of motion formed by this A matrix, you can pull out an equation of motion, the roots of that determine stability. So for this example, we have a transfer function that is closed loop. So we're going to use this first method here. We need to find the poles of the open loop transfer function. This is closed loop. We need to make it an open loop transfer function. So here we have it. What we're going to do is use the feedback equation. So that's g of s over 1 plus g of s. That's how we can simplify this down to one block, because this is just unity feedback here. So when we get this thing, this is g of s right here, right? We multiply by this polynomial to get this monstrosity down to this, and then finally we get this. Great, so this is our open loop feedback, or our open loop transfer function. So we got to find the poles. How many poles are there? There are 3 poles, because the this is a third order polynomial. So there's 2 options for us. We can either use the Routh array. Basically, that's just a way of solving by hand these large polynomials. So we can do like a quadratic equation, right? We can factor this down and get the roots pretty easily, but you know, to a quadratic, I don't really know. I'm not sure. So the way you do that by hand is using the Routh array. If you want to know how to construct this thing here, right, this is the Routh array. If you want to know how to construct it, watch this video. Brian Douglas, that's great. I watched it before making this video. It basically told me everything I needed to know about the lab. Okay, so you construct this guy by hand, and the number of sign changes in this column tells you how many poles are in the right half plane. So it doesn't exactly give you the poles, but it says how many are in the right half plane, and that's important. So I'll talk about why. I'll talk about why right half plane poles lead to unstable systems later on, but I'll give you kind of a refresher. Remember in vibrations how we have, you know, this is the imaginary axis and this is the real axis, and if you have like a dot over here, right, if your pole is like -2 plus 3i plus or minus 3i, right, then you have these guys. Your response is going to look like this, kind of like an underdamped system. If your pole is here at say -3 plus or minus 0 I, it's going to look like this. It's going to exponentially decay. If we're on the imaginary axis, then it's going to look like this. So there's no damping whatsoever. It's just going to oscillate forever. Lastly, if we're, I guess there's 2 more to do. So if we're at like +3 plus or minus 2i, we're going to get a graph that looks like this, so it explodes. And then lastly, if we have like +5 plus or minus 0i, we're going to get something that exponentially explodes. So this oscillates and explodes kind of in an oscillatory fashion. This exponentially just goes to infinity. So the right half plane means that your first number here, your real number is positive. You see that these explode. If it's negative, then they decay, right? This is exponential decay. This is, exponential decay. And when the real is equal to 0, it's not exactly unstable. It's not really stable either. It's kind of like neutral. It's just gonna have the same amplitude forever. So the Routh array over here, the number of sign changes, as I just said, tells you the number of poles that are over here. So there are 2 sign changes. It goes from positive, positive, negative, positive. Two sign changes means that we have 2 poles somewhere over here. So the system is unstable. Now the second way to do this is in MATLAB. So if we know the transfer function, right, the open loop transfer function here, we can say, okay, well, the poles of this are going to be, the poles of this. We just use the pole function. Here's the pole function. We input our system, and here are poles. And as expected, we have 2 poles in the right half plane. We have, and we know that because this is +1 and +1, right? So they would be maybe somewhere over here. That's going to lead to an unstable system. Moving on, here's a for statement. If you haven't seen a for statement before, there's plenty of tutorials on it. I'm not going to spend time talking about for statements, but you're going to need to know how to do them for the lab task. Going on to this next example, as I said, there's another way of finding stability, and that's from an equation of motion. So if we have like an A matrix where x dot equals ax, right? This is a state space. Provided an A matrix, you can pull out the equation of motion, and then the roots of that equation of motion will tell you stability. Those are going to be just like the poles of a transfer function. So if they're in the right half plane, they're going to be unstable. So if you go through this example here, these are the poles of the equation of motion, the characteristic polynomial, and the roots are all negative. So this is a stable system. Great, so let's do an example. Here we have a system, and what we want to do is figure out ranges for A and K, or regions, such that the system is stable. So if we plot K and A, basically we'll have something that looks like this, where up here it is unstable, and down here is stable. So like K, this point here, 4, 1, right? K equals 4, A equals 1. It's going to be stable. This point here, K equals 5, 15, A equals 30. That's going to be unstable, right? Because it's above this line. So that's kind of what we're going to make here using 4 loops. We're going to use 2 for loops actually. So one's going to be inside the other. So what we're going to do is vary K, right? We're going to say K equals, 1, 2, ... And then for each K value, we're going to go up in A until our poles, or at least one pole, is in the right half plane. So the first thing we got to do is we have to turn this into an open loop transfer function, just like the first example. We need this to be R of S goes into one block, coming out of that block is Y of S. So we put this in series here. I'm solving this just by hand. The feedback is this divided by 1 plus this, we get this here. And lastly, we can multiply by this polynomial to make this all nice and pretty and simple. And so that's it. So we got to find the poles of this, otherwise known as the roots of the denominator. So when does S make it such that this term is 0? This expression is equal to 0. So we know there's going to be 4 poles, right? Because this is S to the 4th, and this is our open loop transfer function. So our 4 poles can be factored down to this. So if we know S is equal to the first pole is minus A, the second one is minus B, the third one is minus C, the fourth one is minus D, we can put it in this form, right? Because then when S1 is minus A, this whole thing, right, that's a pole of a system if S is equal to minus A, right? Because this goes to 0, the whole denominator goes to 0, and that's what poles do. They make the denominator 0. So we know that we can turn this into this expression using partial fractions, I think. And then that'll be important in a second. First, I'm going to talk about what does a pole look like. Well, as we explained earlier, there's a real component and there's an imaginary component. And the real component is responsible for the magnitude of the response, and the imaginary part is all about, is it oscillating or not? How much is it oscillating? So if you do like an inverse Laplace on this here, where S is equal to, A plus or minus BI, if you just look at the real part, if you do inverse Laplace, we're going to get this, e to the AT. This is just an inverse Laplace on the real portion of S. And we'll note that this is an exponential. It can be exponential decay or exponential growth, depending on the sign of A. So if A, or our pole, if it is positive, we're going to shoot up. It's going to be unstable, right? It's going to shoot off to infinity. If it's negative, then we're going to be unstable. It's going to decay to 0. This is just what we did earlier. So that's what we're looking for. Is we're going to go through this function here. We're going to plug in numbers for A. Sorry, we're going to go through this function here. We're going to plug in values for K and A. Right. K, A. We're going to see when we solve this, right? When we solve this for a given value of K and A, when does the system become unstable? When do we get poles in the right half plane? And so maybe down here, right, K equals 1, A equals 1, all the poles are negative, right? Maybe up here, all the poles are negative still. When we get here, one of the poles is positive. Well, then we say, okay, we're done, right? We know that above this, we're unstable. Below this, we're stable. Let's continue on to the next K. So that's what we're going to do in MATLAB. So first thing, we're going to say, we're going to only look for A is between 0 and 3. We're going to increment in 0.01. And we're going to look for K between 20 and 120. We're going to increment in 1. When we're plotting, what we eventually want to do is we're going to go through each one. We're going to get a bunch of these dots. And the dot means we're going from an unstable system to a stable system. What we want to do is plot these. So that's what X and Y do. X says at this K value, this is the y says this is the A that is on the border between stability and instability. Okay, so what we're going to do first is we're going to go through the first k, right? So this says we're going to go from 1 to the length of k. So we're going to start here, right? This is our outer for loop. Right, this loop occurs once. You go through the whole loop once. This is our inner for loop. This occurs, we run through this loop every time we iterate this loop. So for k equals like our first value of 0.1, we're going to go a is equal, what was it? Sorry, I think our first k is 20. And then a we're going to iterate through to 1 to 3. And then we move on to 21, and then we iterate a 0.1 to 3, then we move on to k equals 22, we iterate a 0.1 to 3, right? So what we're doing is, okay, we're here, we found this value, we move on to the next k, right, in our outer loop. We do our inner loop until we find an unstable system, right? We keep track of that point. We keep track of that using our x and y variables. We iterate our outer loop. We do our inner loop. We go up, okay, that's where it becomes unstable, and we want to keep track of these points here so we can plot it. So that's what we do. Q here is our characteristic equation. We can solve for that here, right? We solve for that here. We're going to, iterate k and a in a fashion I explained, and then we're going to find the roots for that given characteristic equation. And then we're going to say, okay, if the real part is greater than 0, right? If the real part of the pole is greater than 0, it means it's unstable, and then we'll break from the inner loop, right? That's basically saying we're here, we're going to go up, okay, less than 0, less than 0, less than 0, oh, we're greater than 0, go back down here, this is our value we want. Okay, and then once we've gone through all of the k's, right, now we're here, then we're done. We break from everything, and then we can plot our x and y. And again, our x is our values of k, and our y is our values of a. That are the border between stability and instability. So if we run this, we get something like this, right? So for this region here, we are stable. For this region here, we are unstable. And with that, you guys can go ahead and attempt the lab tasks.